Hello, everyone. This is chapter 15, the beginning of rigid bodies, which we'll be doing for the rest of the quarter. So I wanted to do this video since I wasn't able to have class tomorrow, and I want to make sure that we've kept up. Also, this will allow me to go through an extra example that I wouldn't otherwise have time for. So I do want you to read the beginning of chapter 15, 15.1, 15.2, because it does explain the idea of rigid bodies and how they're different from particles. For one is now we have to look at the thing as both every particle is moving at the same rate that every other particle is. So what I mean by that is if you look at my screen currently, you'll see that the in the upper left you see A1, B1, and what we call that is just plain rectilinear translation. And so we started that at the beginning of the quarter with just a particle moving from one to another, except now our particle is a rigid body, which means that it's a sum of many particles. And so when one particle moves, the other particle moves. So we can define the motion of A1 and B1 as being the same as when they get to A2 and B2. And then in the second picture, you see it's curvilinear motion, which is just motion in two dimensions, in which case, again, the particles have to follow the same path because they're the same object. So rigid body being there's no deformation, there's no bending or fracture of the object that we're looking at. And then we have rotation about a fixed axis. So I think all of these three ideas are pretty easy. Then we get into what's called general plane motion. So this is kind of the way we're going to approach the understanding of rigid bodies. We're going to start off with just simple translation, then we'll go to rectilinear motion, then we'll go to rotation about a fixed axis, and then we do general plane motion. And that could be a little tricky, but we'll work up to that, and that'll be something obviously we're not going to cover in this lecture. We're just going to cover the basics to start. Oh, and lastly, motion about a fixed point. So those are the five categories that we have for this chapter 15. And then general motion, which general motion pretty much combines everything. So I guess everything I've pointed out and that's bulleted here is going to be built upon the previous part. And so this is a repeat of the past slide, but and I probably got ahead of myself. But this was just talking about what we've done so far, and this is what we're going to focus on today. General plane motion, motion about a fixed point, and general motion will come in future lectures. All right. So let's look at this slide. I guess if we go back, I mean, we could go back to this, but essentially what you're seeing here is we know that when A moves and B moves, we can point to A or B relative to A, which means that anytime we have particles moving in a rigid body, they have to form a systematic way of moving, meaning that we can create this triangle where we have our relative positions that stay in the same relative position regardless of where it is in space. So this would look familiar. We remember that the position of B with respect to equals A, distance R, B relative to A. So just like before, we were talking about relative motion, relative velocity. This is the same topic. It's just applied to rigid bodies. And so we end up getting the idea that velocity of B equals the velocity of A. And so the reason this looks this way is because in a particle we can have different locations. So as you see in this upper graph, or I'm sorry, other picture here, we notice that you have RA and you have A and B, and you have a distance from the origin to A and B, and then you have the distance relative to RB relative to A. But when we take the velocity, for example, if this particle is now moving through space, this potato, or just in 2D to start, then we know that whatever the velocity is of A has to be the same as the velocity of B. And again, this is just for rectilinear motion to start. So it makes sense that if we were rotating about A, then B would be moving at a different rate than A would. But that we're not there yet. We're just for simple motion. So that's what you see in the lower picture. You see the motion of the particle moving. And even if it's in curvilinear motion, A and B are still going to be following the same path. And so that's where we get acceleration is equal also. So the takeaway here is that they all have the same velocity, they all have the same acceleration, because when they're moving, whether it's single D or 2D, the particles can't go anywhere else. Now, if we took a rotation about a fixed axis, we can define it with our equation. So we look at the velocity vector. So this velocity vector, the green vector, that would be our tangential velocity. And then about our axis, which is defined as A prime, we have a rotation. And so we can define our R with that angle B and the R vector. So that would be our equivalent of our polar coordinates that we talked about earlier. But simply put, this is just saying that if we want to know the velocity, that velocity V, then that's just going to be the derivative of dr dt. Or we can describe it as omega cross r. So omega is just our angular velocity about the k-axis. So in this case, we're defining k as A prime. And so another way to look at it is at theta dot prime, or just theta prime. That's just the same thing as omega. Now, if we look at something, here's a slab moving in 2D, and these are the equations that we're going to be using for most of this chapter 15 rigid body, is the idea that if you have anytime you're trying to figure out the velocity in meters per second or feet per second, then it's just going to be omega cross r. So whatever that angular velocity is, if you cross it with the distance, then that's going to give you the velocity, which makes sense because the bigger r, the bigger it gets. Now, in 3D, this works really well. Even though we're not going to use 3D, this is an easier way to see it. It's kind of like in statics when we took moments about a point, you could just do force times perpendicular distance. But if you wanted to do a 3D moment, then you would do r cross f. This is kind of the same thing because the velocity could be a 3D vector and r can be a 3D vector. And so if you identify both of them, that will give you the velocity about that plane that is formed by the crossing of those two vectors. So another way to look at it is velocity is just equal to r times omega if you're just looking at where you already know the omega is around the k-axis. So on this question, it asks you, what is the direction of the velocity of point A on the turbine blade? And so intuitively, we know that it's going to go around, so the tip of the blade is going to be going down. So the answer is D. But if we were to look at that, if we wanted to look at it from the graphical or using the vectors, which is more important to understand because this is a simple example, is we look at this. So we see that omega cross r, well, what is omega? Omega is going counterclockwise, so it's a positive, and it's in around the k-axis. So you have a k-axis crossed with a negative I. So remember that when you do your cross products, when you do k cross negative I, you get negative j. And so it points down in that j direction, and we knew that before we even did the problem, but other times you may not be as easy to point it out, but you can always rely on doing the cross products to help you. Now, if you haven't, actually, I'll get to that in a second. So then if we look at another example, This is taking the same idea, only now we're looking at the acceleration. Now, acceleration gets a little more complicated because, as you remember, we have both tangential and normal acceleration. So the tangential acceleration is just simply taking alpha, which is the angular acceleration in radians per second squared, and crossing that with the distance. And then we also have the normal, which we define in the scalar version as negative omega squared r. Now, I don't really like this particular term because it leads people to think that that's always the case. Really, the more accurate way to look at the acceleration normal is what's over here to the right. You see how it says A, because remember that A is equal to tangential and omega cross r, which means that this alpha cross r part, that is our tangential acceleration, and then omega cross r, because what is omega cross r? Omega cross r was the velocity, right? Recall that. So then if you cross it again with if you're basically crossing omega cross v to get this. And then so that if we look at how that cross product works out, that's where the negative sign comes from. But if you just always rely on the fact that it's going to be a negative omega squared r, it can blow up in your face occasionally on some problems. So if we break them down, we have tangential is alpha cross r or omega cross r, and then this is kind of this is in vector form over here to the left, and then this is in the scalar form here, where you just multiply r alpha and r omega squared. So the case to the right side would be if you had 2D and you knew, for example, if you knew it was 6 meters per second squared, and you multiply if you knew it was, in this case, alpha was 6 radians per second squared, then you multiplied it by 5 meters, then you would get 5 times 6, that would be what, 30? I think I said 6. So 6 radians per second squared times 5 meters would give you 30 meters per second squared. So that's all that's saying. Whereas you could just do it if you cross product it that way. This is going to give you the better results, though. But in some cases, we'll show simple examples where this is fine, too. Now here we have the turbine again. And so the answer, I've given it away, but let's explain it because that's more important. So in the answer, we know that what direction is the acceleration? The acceleration always points towards the center. So we knew it had to point towards the center if that was the case. But if we look at our cross products, and this is where, let me stop share, and we look at it this way, we know that we have our turbine blade, right? So there's our turbine blade. Let's draw one of them. And we know it's going this way. So we have an omega k, right? And then it's the acceleration, we know that's an, but we don't know that at that point. We just know that the velocity is going that way. So we know that's our v. So we know that this is equal to omega cross r, and then acceleration in the normal is equal to omega cross v. Okay, so what we did initially up here was we said that omega about the k crossed with r, and so that was what it went this way. So it was in the negative I direction. So negative I. So really what we have is k cross I, don't we? We'll call that L. So we have this, if we called this L. So omega k, write that again. Omega k crossed negative Li. Now, if you don't remember from statics, and this might be really familiar, may not, but I, J, K, just to keep things straight, if you go in this direction, it's always positive, and if you go the other direction, it's always negative. So in this case, if I go K cross I get a positive J. And so it's positive J, but since there's a negative there, it ends up being a negative J, right? And so negative J was correct. It was pointing down, right? So now we have a negative J, right? That's our velocity. So now we go up to here and we want to get our acceleration. So our acceleration then is equal to omega k crossed with negative J. So if we do K cross J, right, we get a negative I because we're going in the negative direction, the clockwise direction. So K cross J equals a negative I, but because there's a negative there, that cancels it. So it's a positive I, which makes sense because we're using this being our positive I and J. All right. So that's the vector math behind it. And as we do examples, we'll go more into this. So if this stuff is a little fuzzy to you, that's okay. It takes practice doing this. Some of you are better at vector math. Some of you, if it's easy, it'll be easy for you. If it's something you haven't fully understood or struggle with, then you may have to do a little extra work. But I don't want to leave anybody behind by just skipping steps. So this is the background. And the beauty of this lecture is you can rewind it and watch it ad infinitum. All right, let me go back. Okay, so that's that. So let's do an example. So go ahead and pause and read this, and then you'll pause, read it, and then I'm gonna go stop share, and we'll go to the there we go. All right, so here we are. So we saw what we had before. We had two gears. And so we're given that A's initial velocity is 15 radians per second. And its alpha A is equivalent to 2 plus 0.006 theta squared radians per second squared. So that's its function. So we want to find omega of B after A revolves 10 times. Okay. So this is much like the properties in linear. So we still use kind of the same thing. So recall that VdV equaled AdX. That was a common relationship we used. And so we can write this then as we know our relationships. And so what we can do is we can write this as the integral of omega dw. That's our VdV. And that's going to equal our integral of alpha d theta. So same thing, just different way of looking at it. So we'll write this. So we know we're going to go 15, right? That's our initial radians. And then up to omega. And then we have from 0 to theta. Okay. So we know that this is our initial omega, right? Like we said, up to wherever it's at. And then we want to go from 0 to however many radians we have to go. So we'll go ahead and write that in. Integral 15 omega w d omega, or omega d omega. So they do look like W's, sorry. 0 to theta, 2 plus 0.006 theta squared d theta. And so what we end up with is a fairly easy integral. We end up, when we evaluate this, that's just omega squared. So we end up with omega squared over 2 minus omega squared over 2, squared not, over 2. And then, so we know 15 goes into there, and that equals 2 theta plus 0.002 theta cubed. All right. So we end up with, when we simplify this, we plug in the 15 squared there, and we end up with omega, I guess we should call this omega A, or we can just leave it, omega squared equals 4 times, so I'm basically multiplying both sides by 2, 4 times theta plus 0.004 theta cubed plus 15 squared. Okay. So all I did was multiply both sides by 2. This plugged in 15 for omega naught, making it a 15 squared, moved it over here. So now I have this. All right. So if I go ahead and plug in, now one of the things, I have that, but it says find omega b after a revolves 10 times. So that's 10 revolutions. So remember, 1 rev equals 2 pi. So 10 revs equals 20 pi. All right. So what we'll do then is we'll just plug in, and we'll know that omega equals 4 times 20 pi plus 0.004 times 20 pi cubed plus 15 squared, 225, and all of that to the 1/2. And so we end up with WA, because this omega was for omega A, right? And that's going to give us a value of about 38.3 rads per second. So one of the, we found omega A, right, because we were given its acceleration. So then the question is, what is omega B, right? Because we want to know what omega B was after 10 times. So remember that the relationship, and you're probably seeing this in your CE204 if you're taking it, but we know that omega A times its radius A equals omega B, sorry, omega A times B equals omega B times RA. So no, the way to write it is omega A over RA equals omega B over RB. So we end up with omega A equals 175. I'm sorry, not equals, times 175. That equals omega B times 100. So we plug that in down here, and omega B is 21.9 radians per second, which makes sense. It's bigger, so it should go slower. Sorry about that. So this is your relationship here. Cross multiply, we get this. Plug in that, get that. All right. So you can always pause and go back over it, but it's pretty straightforward. So the only reason I did this example is I'm trying to get you used to thinking in thetas now, because that's where we're going to be for this immediate part of the class. Okay. Let's look at another example. Now, this example too uses the idea of R or omega cross R to figure out what we have for velocity. So this is a fairly easy one, but again, it's just getting you used to these relationships. So you go ahead, as I said, read it, and then let's go ahead and do the problem as you can have the power to pause it. So here we have this assembly, and so we're rotating. This is point B here. So it's rotating about AB and at a rate of 10 readings per second. So the whole thing is rotating. So imagine this is like a line and the whole rotation. So this thing's coming up. So E is going to have a different speed than, say, I think this is point C over here. It just depends how far it is from the axis of rotation, which makes sense. It might have the same omega, but as we've learned that the farther you are from the center of rotation, the larger your tangential velocity is. So all these things, getting comfortable with them and being able to know them secondhand is what's going to make you successful. So this stuff here is just preliminary. Then we'll get into the more complicated stuff soon enough. Now, in this case, what we know that we're given, we want to know what omega, and so omega as a vector is going to equal omega as a scalar times lambda AB. So you might remember this from statics. So here's my omega vector, because in this case, because of the nature of this rod, it's going to be a three-dimensional omega. It's going to have a component just like a three-dimensional velocity. So lambda AB, just this is stuff you can from statics. We know that lambda AB is going to be 0.5 I. That's just going from A to B minus 0.225 J plus 0.3 K. Everything here is in millimeters, and so we're just converting it to meters. And then over 0.625. I mean, it doesn't matter. It'll still come out the same. So what we end up with then is when we multiply omega and we multiply through with that, that's going to equal, since it's 10, it's basically just going to increase. It's just going to increase it by whatever these factors are. So 10 times, and then that's just 0.5 over 0.625 I minus 0.225 over 0.625 J plus 0.3 over 0.625 K. All right. And so we end up with omega is just equal to 8I minus 3.6 J plus 4.8 K. So remember, we're trying to find omega, and so we know what that is. That's given. So not given, but we're given that it rotates about the AB axis. But so now we have this, right? So we found omega as a vector in radians per second. Now, we also want to know what the velocity is. So this is omega E. What is velocity E? So we know that is going to be equal to omega cross R. Now, what's the R? Well, it's going to be any point, since it's about E, it has to, your vector has to go to a point on here, because that gives us our R, how far away we are, just like in a moment, R cross F. Only here it's omega cross R, it's reversed, but it's still the same concept. So we know the best way to get from R, E relative to B, which means we go from B to E, and that's just going to equal negative 0.3 K. And so with our axis, of course, this being the Z, this is the X, and this is the Y. All right. So we've got we've got that, we know that. So since we have this up here, then we just write it out. VE, notice that going to equal, it's going to equal 8, negative 3.6, 4.8, and then 0, 0, negative 0.3. So when we do our cross products, which I'm not going to repeat because you guys are experts at cross products, it's going to give us 1.080 I, proper sig figs, plus 2.40 J meters per second. Just like that was radians per second, although I admit I didn't do the right sig figs there. So this technically should be 8.00 I minus 3.60 J plus 4.80 K. There we go. Now I have the right sig figs. Okay. And then we're also supposed to find our acceleration. Now, so we know that acceleration is normal and tangential, but because we're told it rotates at 10 radians per second, that means it's constant. There's no tangential acceleration, but we still have AN or A normal, and that's what we got to calculate now. So now we need to find the acceleration, as I said. So we have that. So the important thing is to always remember the acceleration tangential is oftentimes 0, but only if V is constant or omega is constant. So constant omega. Now, I mean, I guess unless you're talking about a different point on the radius, it's going to be the same. But so we want to then recognize that our acceleration total is always going to equal the acceleration tangential plus the acceleration normal, right? And so you add these vectors together to get the total acceleration. Now, you remember that we did do a squared equals an squared plus at squared, right? That was magnitudes. So that's like Pythagorean theorem. That's only when we had magnitudes. When we have vectors, we just add the vector components. And we'll do a lot of that in the coming lectures. So in order to get our acceleration normal, we know that's just going to be omega cross our V, which we already calculated, right? We have V and we have omega. So we basically have 8, negative 3.6, 4.8, 1.08, 2.4, and 0, right? That's how we define omega and V. So if we do our cross product, we end up with acceleration equals 11.52 negative I plus 5.18 J plus 23.1 K. And that's in meters per second. Okay. So again, just manipulating some numbers just to get you used to going between radians and meters, or distance, linear distance versus angular. Okay, so one more example, and then that'll be it. This is probably more time than we would have had in lecture. And we'll mop this up a little bit in the next lecture. But we're going to keep going through this over and over again. So it's going to seem a little repetitive, but that way, when we start doing our relative motions of rigid bodies, it'll be easy for you guys. All right. So here, go ahead, pause, read this, and go ahead and work on it since you've read it. All right, so the load omega is a load, sorry, W, not omega. So hazards. So my weight is raised 20 feet. Now, A accelerates at 100 to 120 RPM in 5 seconds, then maintains constant speed at 120 RPM. So we want to know A, number of revs to lift load. Okay. So we want to raise it total. So how many revolutions to raise it 20 feet and how much time? All right. Okay. So now I've given you a couple things. The ratio, there's gears. I haven't drawn the gears, but this is the only important part, is that if we go from the center of gear B to the actual outside of the gears, that's 18 inches. If we go to just the inner radius, that's 15. And A has a radius of 3. Okay. So we know that gear B must move. So the total revolutions of gear B equals the height over the radius of B. So that's equal to 240 inches, which is 20 feet, right? 20 feet is 200 equals 20 feet, right? And that's over the radius of 15 inches. So gear B must move this many. And so that's 240 over 15. So that equals 16 radians. All right. So now we also know that distance-wise, S, that equals R theta. So that's no different than saying if I had, something like this where that's theta and that was my S and this was my R, then remember R times the angular distance gives us that total position. Okay. So another way to look at it is we know that S is going to equal 18 inches times 16 radians. So that's a total of 288 inches. And then if we want to look at A, A would also have to move that far. So in case of A, it would be 3 inches, and that would have to be 96 radians in order for it to move 288 inches. So whether or not we need this or not, it is up to, but what I did is I just essentially, I knew this is how far, I knew I had 16 radians, I knew I had a radius of 18. So then I wrote 288 equals 3. So how many radians is that? It's 96, right? Okay. So now we know that RA theta A equals RB theta B. And so that's kind of where we got the theta A was 96 radians. So I kind of went full circle. So we have theta A is equal to 96 radians. So I guess I could have consolidated all this. I kind of went off on a train of thought. So I got this, but then we could have done that. So we have 96 radians for the 16 radians that theta B went. Now we want that because we want to know the total number of revolutions of A. So total revolutions of A. So that's going to be what? It's going to be 96 radians divided by 2 pi radians per rev, right? So that gives me about 15.28 revolutions. All right. So now we know that omega naught was 0 and omega final was 4 pi. Okay. And so where'd we get the 4 pi? That's Well, it told us a speed of 120 RPM, right? So 120 RPM is the same as 4 pi radian per second. So how did I get that? Well, you know, it's 120 revs per minute. And then you're going to multiply that by 2 pi over 60. So that's our conversion. So 2 times 2 pi is 4 pi. So just remember that that's your conversion. So RPM to radians per second is 2 pi times 60. Okay, so remember that. So we have this, we have that. So now what we can do is, because we have these start and stop point, then we can, and we're told that it goes to alpha in 120, from 0 to 120 in 5 seconds. We can go and use our kinematic equations. Now, I know I haven't mentioned them yet, but the kinematic equations are the same, and you should remember those from physics. But if not, we know that just like V final equaled V naught plus AT, omega final equals omega naught plus alpha T. So we can then write essentially that's 0. So we know that it's going to be 4 pi divided by 5 seconds gives us our time. And so we have what? Radians per second and over second, and that's going to give us our radians per second squared. I'm sorry, that's going to, no, this is 5 seconds. Yeah, I'm sorry, that means it's going to give us our radians per second. No, these are just radians. What am I thinking? So those just disappear. And so we end up with the time. And, oh wait, what am I doing? I'm sorry about that. I'm having a, I guess it's Saturday, it's Sunday afternoon. So sorry about that. It should be 4 pi over 5 seconds. And that gives me alpha, right? Radians per second squared. So that gives me alpha is 2.513 radians per second squared. Okay. Now we're not done yet, because remember what it asked. It says the number of revolutions to lift load. Okay, so we have to figure that out, and the time. So what we do now is we know that theta A equals theta A naught plus omega naught T plus 1/2 alpha T squared, right? Just like X equals X naught plus VT plus 1/2 AT squared. This is just alpha. So if we plug this in, we get theta A is equal to 1/2 2.513 rads per second squared times 5 seconds squared. Okay, so that gives us theta A is equal to 31.42 radians. All right, but remember, how many radians did we need? We needed a total of 96 radians, right? And so we needed 96 radians. So we have 31.42, but we still have more to go. So 96 radians minus 31.42 radians equals 64.58 radians. All right, so that's how much farther we have to go. So how fast is that going to go? Well, so we started, we accelerated, we got to full speed, right, which was 4 radians per second. So now we have to figure out how much time that is. So what we do is we say, well, we know that the omega is equal to, or I'm sorry, theta is equal to omega t. So we can calculate that. So we want to know the time. It's just going to be equal to theta over omega, right? And so if we plug that in, we know it's 64.58, and we know the speed. So this is no different than saying t is equal to x over v, right? So meters over meters per second. So this is just in radial. So 64.58 radians over omega, which was 4 pi. And so that gives me a total of 5.139 seconds. Okay. So we found out then that's 5.39. So let's go back. Remember what the original question said. It said, the number of revolutions to lift the load, right? So we figured that out. That was 15.28 revolutions. That's how many it was going to lift. Then after that, we wanted to find the time to lift the load, right? So we know we had 5 seconds accelerating. So in that 5 seconds, we did 31.42 radians. And then in the next 5.139 seconds, we did 64.58. So 5 seconds did us 31.42, and 5.139 gave us the additional 64.58. So now we had our 96 radians, and we had a total of 10.14 seconds. All right, so 10.41 seconds to do 96 radians. All right, hopefully that's clear. So I would definitely look in the book, look at the different relationships, but we are going to do more of this on Wednesday. So I hope you guys have a good day. I will see you Wednesday. There will not be office hours tomorrow. I will post the next assignment, and I'll send this all out in an email. Thanks, you guys, and I'll see you soon.